Okay, in this presentation, I will cover a few topics here. First, I will give you an introduction where I will be discussing the concept of GPR. And then I will talk about the ground penetrating radar applications, and that's including how to measure the pavement thickness, as well as a new technique for measuring the density of the pavements using GPR, and then summarize my discussion. So before we start here, we talk quite a bit about non-destructive testing. So what is non-destructive testing? In a simple way, is trying to detect any defects or distress within a materials or within a pavement section or a bridge or any infrastructure without doing any damage to that infrastructure. A good example for that, if you go to a dentist and you do an x-ray for your teeth, you cannot see a decay, but the x-ray will show you if there is a decay in your tooth. So in a very simple way here, we'll be able to see what we cannot see in naked eye. So there is many different methods that we use in civil engineering, and I'm going to start with the simple methods and go up here. Simple method here is to use the chain drag that we usually use on bridges, and this is to detect delamination. So when we drag the chain, if we hear a different echo, that will tell us here that there is a delamination or there is a void in the bridge. This technique here by itself is a non-destructive technique. Another technique is to use a stress wave, and the stress wave, it's affected by the poisonous ratio, the modulus, and the density of the material. So if any of these three properties in the material changes, the velocity of this stress wave will change. Of course, they are different stress wave. It could be longitudinal, shear wave, or what we call them P and S wave, as well as the relay wave. So it depends on the wave that we are using, and there is a relationship, as I said, with the density and the poisonous ratio and the modulus of the material. We will be able to tell something about the strength of the material or the structural capacity of this material. A good example for that is an impact echo. This is a simple technique here where you are using a ball, and in the ball you hit it on the structure, and the wave will go through the structure. You have a receiver, you pick that wave, and then you take it from the time domain to the frequency domain, and you can measure thickness or you can detect the defects in the system itself. Another way is to use an ultrasonic. An ultrasonic is, again, a wave, a stress wave or ultrasonic wave that it's moved into the structure. And if there is a defect or there is a change in the structure, the velocity will change. A good example for this is usually we use it to measure the curing of the concrete or the strength of the concrete. In this particular example here, we are using it to find the conduit or the pre-stress conduit or pre-tension conduits that you have in a structure using the ultrasonic. The one that I'm going to be talking more about is the electromagnetic waves. The electromagnetic waves is going over a big range of frequency or wavelength. The wavelength can be from hundreds of meters to much smaller than the nanometers. So we are talking here about a big range, and I'm sure you are familiar with many of these areas. For example, the radio wave. The one that I'm going to be talking more about is the microwave, and the microwave usually is in the range of the centimeters, and that's reflect to the gigahertz, and that's the one that I will be spending some time. If you look here at a smaller wave, that's the infrared. And if you go a little smaller than that, that's the visible one. And then you go to ultraviolet, X-ray, and gamma rays. So to give you some examples about this that we use in the asphalt concrete is the infrared. So the infrared is used sometimes to detect segregation in the asphalt concrete. The way it works that if you have different materials, or materials that it's cooler than the other one, then you're going to end up with some segregation when you put it in the field. So you can detect this change in the temperature during the loading of the asphalt concrete on the truck, which you cannot see here, of course, and you're going to be expecting that you may have some problems when you place it and you pave it. Another example is to use the X-ray radiology. This is an example here where it's used in order to detect the fibers in the concrete and the orientation of the fiber of the concrete. So with this introduction here, that will take me to talk a little bit about the ground penetrating radar. So what's ground penetrating radar? In a simple way, it's the same as the radar that we are using for detecting airplanes. So what happened here is you are sending the electromagnetic waves, it hits an airplane, and it comes back. So we know that the speed of the electromagnetic waves is the same as the speed of the light. So if we know the speed of the light and we know the time that it takes to hit the airplane and comes back, we will know how far that airplane from us. So it's a very, very simple concept. So we use this concept now to apply it for other applications in transportation, such as in geophysics, we're trying to estimate the structure of Earth sediments, and usually this is at a very, very deep. Sometimes we're talking about thousands of feet, and that's going to require from us using a very, very low frequency. Archaeology, sometimes to locate buried archaeology structures. Also for safety, to locate landmines, we are using electromagnetic waves. Of course, in landmines, usually, supposedly, that the landmines, they should have a little piece of metal, and that's how they detect it. But of course, if you're trying to produce landmines that it doesn't need to be detected, you don't need to put that metal according to the international law. But in that case, you detect it indirectly by the disturbance that's happening when you are placing this material, or you have a material, a body, that it has a dielectric constant different than the surrounding. And I'm going to come to the dielectric constant here in a minute. Then we come to the civil engineering, and we have been using it quite a bit for buildings, bridges, pavements, railroads. So before we start talking about the GPR, there is a couple of terminologies that I wanted to make sure that we share here. The first one is the permittivity. Permittivity is simply, it's a measure of the ability of material to resist the formation of an electric field. And usually we consider the air as a reference. So instead of dealing with the permittivity, we deal with something, we call it the relative permittivity, which means that we reference everything to the vacuum or to the air, and sometimes we call this the dielectric constant. So the dielectric constant, it's actually the relative permittivity with respect to the vacuum. So this is here the equation, which is the dielectric constant or the relative permittivity, and the permittivity here is divided by that of the vacuum. Please notice here that I will be talking about the dielectric constant as an absolute, but I wanted to emphasize here that the dielectric constant is a complex number which has two parts. The real part, which has to do with the storage, and the other part, which is the phase part, which has to do with the loss. Example of that is if you are using the microwave at your home, you take the food and put it in the microwave. If you have your food completely dry, you will find that it's going to take a long time to heat it. But if it has a little water in it, because the water is a very lossy material, the food will be heated much faster. On the other hand, if you get your sandwich wrapped with a foil, then you're going to be getting sparks everywhere. And the reason is, anybody tried that? Oh boy, a lot of people did. Okay. So this means here that the foil is a complete reflector, so it will just get the electromagnetic waves completely reflected from that sandwich. Okay? So let's keep these few things here in mind, which is the water, that it's a very lossy material, and the metal or the foil is a complete reflector. Now, if I take the water and make out of the water ice, then I'm structuring the water. If I structure the water, then it will not be lossy anymore. So compare here a dielectric constant for the water of 80, which is very, very high. If you structure it and you make it as an ice, the dielectric constant will become very, very low. It's even close to 1 or close to the vacuum. And that's why if you have a frozen food and you're trying to heat it in the microwave, it takes much, much longer time. Is that true? Yep. Okay. So this is here a small table, just will allow us as we go here to understand why materials behave differently. First, the air, we said this is our reference. We give it 1. The water is a very lossy material, and it has a very high dielectric constant. So 80, it's a very high number when we consider the dielectric constant. Then you get the concrete. When it's completely dry, it goes from as low as 3. If you get into a concrete that it has an aggregate, that it has high iron in it, then the dielectric constant can jump up to something like 20, 18, measured, especially the concrete that they are using for nuclear plants, for example. Another thing here, if you have, free water in the concrete, that will increase the dielectric constant. If the water is attached, then the dielectric constant will be low. So remember here, the water dipole got to move when it's applying the dielectric constant in order for the dielectric constant to, when applying electromagnetic waves, so the dielectric constant will be high. Asphalt concrete, again, it's from 3 to 10. Asphalt binder is almost constant, which is really good. So it's around 3. Then you get into the limestone, granite, and the granite is always lower than the limestone, and that will help us in our analysis later. Then you get into materials like the silt, clay, and the clay is the toughest, actually, because sometimes the clay, it has a water that it's completely adsorbed, not absorb, adsorb, which means that it's chemically attached to it, and that doesn't allow it to move that much. So the dielectric constant will be low. But if the free water in the concrete, then in the clay, then the dielectric constant will be high. So we're going to be looking into two things here. One is the propagation, and the second is the scattering. The propagation is when the electromagnetic waves go through a material, it will propagate through the material. This propagation speed, it depends on the dielectric constant. So this is here a very nice simulation where it shows that you have a dry sand and the dielectric constant is 6. So the propagation, it's going to be much faster than if you compare it to a saturated sand where the dielectric constant is 25. Now, the speed here is always taking as the speed of the light divided by the square root of the dielectric constant of the material. So, for example, if you look at 6, you take the speed of the light, which is 10 multiplied by 10 to the power 8. It depends what units you're using, and you divide it by the square root of 6, and that will give you the speed of the electromagnetic waves inside the dry sand. Then we have another thing, which is scattering. When you send your electromagnetic waves, at the minute that it hits a material that it has a different dielectric constant, some will be reflected and some will be propagating. So for example, if you are using the GPR and you send your electromagnetic waves, some of it will go to the surface and reflect, and some will go to the surface and enter. And the entrance of the angle is always kind of a little different than the angle that it's be reflected, and that will be important for us as we discuss this later on. So for structures, we can use this scattering to detect segregation, delamination, reinforcement. For pavements, we can use this for detecting layer interface and internal distresses. And for railroad ballast, we have been doing quite a bit on detecting the fouling, which is the presence of the soil and contamination in the ballast itself. So let me go back here and talk about the GPR types. The one that you have here is the pulse, or called sometimes impulse GPR. There is other type of GPR, such as the synthetic pulse GPR and the frequency modulated GPR. And these are different than the impulse or pulse. The pulse is used because we are interested in detecting the interfaces. The other one, they will allow us to look at the bulk. So we will not be discussing this today. So this one is the most common one, and it transmits a signal in a short pulse that depends on the frequency that we are using. It's in the range of 1 nanosecond. And the principle is simply you are submitting or transmitting a short pulse here, and you are recording the reflection. And the reflections could happen from the surface. It could happen from any of the interfaces that you have in the pavement section. So for the GPR antenna, we have two types. One is the ground couple, and the other one is the air couple. The ground couple is the one that it's in contact with the surface, and there is usually a little concern with that, which is the ringing that you may have from the surface. And another concern is if you put it on a vehicle, you cannot drive this vehicle more than 10 miles an hour. And usually it's at a lower frequency. The other one is the air couple, which I think that's the one that you have. And the air couple is one that you can put it above the surface, which is the picture here. And this one, usually, it goes 1 gigahertz, 2 gigahertz, and even a little higher than that. And we have two types also as to the antennas. We have the monostatic, which means here that you have the transmitter and the receiver in the same antenna. And you have another one where you have the transmitter and the receiver two separate. So if you look at this antenna here, I can use this antenna here as monostatic as well as biostatic, because there is a transmitter and receiver here, and I can use each one of them as a transmitter and receiver too. So let's see how the GPR measurements is done. So you have a distance measuring instruments, which is attached to the tire, or you have a GPS or a combination of both. These will be sent to a modulator which generate this pulse and send it to the antenna. The antenna sends the pulse, and when it gets to the antenna, it sends it to the ground. When it gets to the ground, some of it will penetrate inside the pavement, others will be reflected from the surface. It keeps penetrating, and it will lose some power as it's penetrating until it reaches another surface which has a different dielectric constant. Then some will penetrate and some will be reflect, and it will continue. After that, it will go back into the system, and in the system here, you will see some figures that we're going to go through it here in a minute. So the GPR direct and indirect application is for in-service structure evaluation. We can detect moisture because I said moisture has a very high dielectric constant. We can detect a distress because the distress will be having a different dielectric constant. We can detect reinforcement very easily because reinforcement is a complete reflector. And we can also use it to evaluate the rail road ballast. Today, I will focus on 2 points, which is the layer thickness estimation, as well as the density assessment, which is something new that we have been working on. So let's look at the detection of the reinforcement. These are very, very simple to detect. So if you have the radar or the GPR vehicle driving on top of a reinforced concrete, and you have the rebars, as it's moving, you will start having these concave shapes underneath, and this is because of a complete reflector. Now, this concaves here is not because the rebars are circular, it's just because the way that you are approaching it. So this is the GPR, it's far from this. As it's getting closer, this will become closer, closer until it reaches the system here, and from that we can calculate what is the cover depth that you have on top of the reinforcement. So here's 2 advantages. One is I can detect where do you have a reinforcement in a structure, and second, I can measure what's the cover depth, which is really important for the rehabilitation process. So this is here an example where an estimation was of the rebars, and you can see the error is very, very low here. These are the different measurements that was taken from a road. So the measurements actually, the error that you get from these measurements, it's within the variations that you have from the cover depth itself. Here's a good application where a steel mesh is used for reinforcement of pavement, and if you want to check if the steel reinforcement that it's used for overlays is placed accurately, you can use GPR. Here you can see that some distortion happened, and this distortion is going to result in some distresses later on. Dan Ryan Bridge is one of the longest bridges that we have in the States. It's like, it varies actually how you measure it, but let me focus on the one that we dealt with, which is 4.6 miles. And one of the things that they approached us to look at is what's the cover depth, because the cover depth going to dictate the rehabilitation technique that they are using. And if any one of you have been to Chicago, this is a very, very busy bridge that they cannot close. So the only way to do it was with the GPR. So we were driving early in the morning, and we did it like for 2 days, each day very early in the morning for 4 hours, and we covered the whole bridge driving at 45 miles an hour. And we did not have any traffic control. We have a safety vehicle behind us because we're driving at 45 miles an hour. But ultimately, the results was very simple. We told them what's the cover depth. According to the DOT, they were saving millions just because of that. Of course, they went back and they took a couple of cores just to verify the results. Another thing here, sometimes you are having an overlay and you don't know what's underneath that overlay. By seeing cracks on the surface, especially in cold regions, you don't know if these cracks are reflective cracking or low temperature cracking. A GPR can tell you where you have a reinforcement underneath a joint, and that will tell you if this crack that you have is a reflective cracking or if it's a low temperature or thermal cracking. And we have a study and a report on something like this. Another thing is sometimes when you have joints and you put what I call them band-aids or strips on top of the joints before you place the overlay, I can tell you, you go to projects and sometimes you find these things are placed and in many cases they are not. So the GPR can tell you for sure if this has been placed or not, as you can see here. This is the reinforcement or the dowel system, and this is here one of the geosynthetics material. Actually, it's called ISAC. It was developed by one of my colleagues at University of Illinois, Barry Dempsey. So we can easily detect the presence of this material. Another thing that it can be used is for the evaluation of old and new bridges. This is an old bridge. An old bridge, we don't have any design about it. So GPR can be used on the top in order to see the reinforcement on the top and the cover depth, and we can go from the bottom too. And from the bottom, you can also find where the reinforcement, the location of the reinforcement. At this time, we were using this grid system, but this is now also accompanied with a GPS, so you can find the reinforcement accurately. This is another interesting project, which after they built the abutment and they were trying to put the girders in, the girder fell off and a couple of people got killed actually. So when the girder fell off, they didn't know if this abutment is safe or not. So the only way is to go and check it. So GPR was used in order to check the reinforcement. Actually, we used along with that an impact echo as a verification too. So we were able to know where the distress is and identify them for the agency in order to find out, is this solid, they can use it or not. So we found that it was safe, the project is completed. If they weren't sure, that could have been a lot of money because they have to take the whole system out. So let's move gears now to the pavements, which is the main topic here. Just gave you a little bit of background how the GPR can be used for different transportation infrastructures. For pavement, it's very simple. This is actual data that you are getting, but you don't get it as nice as this all the time. So we're going to look at the nice one as well as the not nice one. So here's when you send your electromagnetic waves, you are moving from a dielectric constant of 1 to a dielectric constant of, let's say, 3 and 4. So you're going to have a big difference. This big difference, I'm seeing it with this. Then it propagates down. As it's propagating down, it moves to another material, which is the base. The base material, have a different dielectric constant, so you're going to have a little different reflections, and you can see it here. Let me emphasize here, if you have a base material that it has the same dielectric constant as the asphalt concrete, GPR will not see it. So we're not seeing materials here. We're not detecting the strength of the material. We are seeing just the difference in the dielectric constant, period. So even if the materials are different, if they have the same dielectric constant, you will not be able to see them with the GPR. So if I take that pulse that I just collected here from this one and stack them next to each other, this is one pulse. If I drive my van and I take a pulse every 1 inch or 6 inch or 1 foot, whatever you want, and take these pulses and stack them together, you will see something like this. So all what I'm doing here is I'm stacking all my pulses together. If I stack all my pulses together, I will end up with something like this, that anybody can look at it and can say, wow, these are different layers. So this is very, very simple. But the second part is how I'm going to be detecting now or determining the thickness for each layer. So the method that it's used right now is you look at the amplitude on the surface, and you put a copper plate so you can measure the complete reflection, which is the pulse that you're sending if you have a complete reflection. So you know the pulse that you send, you see the reflection that you are getting from the surface, you put this in an equation, and that will give you the dielectric constant. So here, the dielectric constant that you are measuring is the dielectric constant of the pavement, but it's coming from the surface. And that's where I warn here about this. If the pavement is new, that's fine. If the pavement is old, then you have to know that there is an error in what we are doing. And that's what usually used for people who are trying to determine the thickness, that they are usually use the reflection just from the surface. So if the surface is aged, the dielectric constant is going to be different than what's underneath the surface. So from that also, the surface reflections will be able to calculate the dielectric constant. As the dielectric constant increases, the surface reflection amplitude, of course, will increase. So you are expecting a reflection from a concrete structure higher than the reflection that you are getting from an asphalt structure. But if I wanted to see the dielectric constant or to see the whole layer, I need to do something a little different. The only way I can do that is to go to each road and parry a copper plate. And that's what we did when we built the Smart Road when I was at Virginia Tech. I put 36 copper plates, because I have 9 different materials, 9 different designs, and that allow me to come up with a calibration. And you can see here, this is the copper plate. It's a huge reflection. As you are going down, the reflection is less because I'm losing power, okay? If I look at this from a theoretical point of view, and please don't get offended, it's just in a simple way, is that you send your electromagnetic waves, some get reflected. The stuff that doesn't get reflected, which is 1 plus rho, it will go through and it will lose some, which is the transmitted one. When it gets here, it will reflect it, and then it will lose some, and so on. So it's just keep going like this. We found that if you get these two, that's enough for you to collect all the data. But there is a problem here. Am I willing to put a copper plate in each road I'm building? That's impossible, right? So we need to think about something a little different. So one way to think about it is to use, instead of 1 antenna, 2 antenna. Please remember here, because the equation is just very simple. The equation, if you go with this, I'm not going through the whole thing, but it's very simple here. It's the same. I'm adding this here, this part to it, where x is something I know, and then t is the time that it takes for this wave to go through here and come back here, and the unknown for me is the depth, okay? So if I'll go through this, I'll come up with the dielectric constant, that it's function of the speed of the light, and this is T2, which I will know, and T1, because I measure these things as I'm sending and receiving my electromagnetic waves, and X is something I decide, which is the distance between the 2 antennas. So that will make it very easy for me to resolve. The problem is, in real life, we don't have this antenna. So I have this, but this is going to make it very, very difficult to do it in real life. So we went ahead and we advanced this a little better. So we came up with what we call it the modified CMP technique, where we use an antenna like that you have, and one which is ground contact, and that's maybe you have. Do you have a ground contact and air contact? Both? Okay. So if you have that, that something can be done. Again, I know what's the distance x naught, but the only thing that I don't know here is x1, because I don't know when this is going to enter the pavement. And I don't know d1. So again, I'm going to go through the process. One of the things that I'm going to be using is the Snell's law, and the Snell's law is telling me that the sine of the angle that it comes here multiplied by the square root of the dielectric constant of this material going to be equal to the sine of the reflected angle here multiplied by the square root of the dielectric constant. So that's the Snell's law. So I'm using this here, and it's very simple. If I go to x1, what's left from x1 is this distance from here to here, and this has to do with the d naught. So I have x naught, which is equal to x1, and then it's d naught multiplied by tan theta, which is the incident angle here, and I have one here and one here, so I multiply it by 2. So just very simple. I think you have access to my lecture, so very simple. We go through these equations, and we come up with the dielectric constant, that it's a function of the sine theta I, and sine theta t. Sine theta I, we need to work on that. So there is an algorithm that we can work. First, we can measure T1 and T2, and from that, we can come up with the reflected angle. Then we use a numerical solving technique to come up with theta I, and after finding theta I, we can use Snell's law to find the dielectric constant. So here's another technique that will allow me to find the dielectric constant. If I find the dielectric constant, I find the thickness. The most advanced one that we just developed here, which we call it the extended CMP, and I promise here no equations. This one in particular now, I'm using the two antennas, which they are above the ground, that will allow me now to drive at a highway speed. So I can drive at 60 miles an hour while we are measuring the dielectric constant. I'm going to emphasize here why we are doing this, because if I measure the dielectric constant just from the surface, that will be okay if it's a new pavement. If it's an old pavement, then that will not give me good results, and that will give me significant error, because it will be just the surface dielectric constant. So after I collect the data from the GPR, I wanted to analyze it. So the first thing, I need to clean it, which is pre-processing, and then identify where I have an interfaces, and then estimate the dielectric constant. So this is typical data that you get. This one here is what we call it the coupling. The coupling comes from the talk between the transmitter and the receiver. And these two antennas, they talk to each other. They talk like this, and they talk also, if it's one, with what we call it internal reflection. So we wanted to clean this. The way to clean this is just you take your antenna, you flip it to the air, and then they are still talking to each other. So you take it to this figure here and subtract it, so all the coupling is gone now. Another thing is if you are collecting data and you are on your cell phone or you are passing a tower or whatever, all this interfere with your data, so you need to clean it. So this is, I'm not sure here if this is here, this is all noise, and this noises can really affect your analysis. So what we do, we can use some filtering and take all this stuff out. So you can see now this is much, much cleaner after taking the coupling and after taking all the noises that you have here. If you look at a raw GPR data like this, you have layers like 1, 2, 3. And if you look at the data as a pulse with amplitude, you can see here the difference. This is a pulse where we identify layers. The way in which I do it in the software that we have, I'll say that anything less than 1 foot, I don't want to even to look at it if I'm measuring thickness, because in that case, it could be because of any internal things in the pavement. So we need to define for how long you're going to have this, what we call it, interface. If I look at this from the time domain point of view, I can define them now as different layers. If I'll use the approach that I just presented in this one here, I can calculate the dielectric constant. If I calculate the dielectric constant for the 3 different materials, I simply can come up now with the thickness for the pavements. The difference here is the thickness that I come up with for my pavement, it's based on actual dielectric constant for each point we are measuring. So it's not an assumed value. So the problem that we have right now in the current GPR system is you always assume a value, or you calculate the value from the surface reflection and use it, and that will lead to some cumulative errors in my opinion. Now, here's some of the tricky things. This is here data that we collected from a road that it has a wearing surface, base layer, OGDL, or open graded drainage layer, and a base layer. When we look at this one here, somebody gonna look at it and say, I have here the subgrade, okay, and of course this is related to the time, how long it takes to get there. And this is where I have the base with the subgrade, but I don't know what's happening in this area here. It's definitely 2 kind of amplitudes on top of each other, and the same here, 2 things came up on top of each other. A simple way to overcome this, I think that you guys are doing a lot of work in FWD, just use the same concept. The same concept is I'm creating a wave, and this wave here, I'll make it similar to the wave that I have, and I look at the least square error to make sure that it's matching the wave that I have, and then I say, how did I come up with this wave? I have 4 different layers. Give me the different dielectric constants that I have for these different layers in order to match the wave that I got. If I got this going, I will end up here telling me, oh, wait a minute. This is the wave that you have. This is another one where you have between the wearing surface and the BM, but this one goes like this. And this one here is between the OGDL and the base mix. So if I add these 2 things together, I end up with something like this. So this now, I can even have sophisticated signal that I'm collecting from the GPR, and by analysis, I can now define a very thin layers of asphalt. But that requires some work, but that sometimes is very important if we're doing some quality work to quality control. This is, for example, typical data from 18 pavement sections, concrete asphalt, the age is up to 25, you don't know nothing about them. And the accuracy was within plus or minus 3.7. If you have a very new pavement, the accuracy it can be as good as the cores that you are getting, because the dielectric constant doesn't change much and it's constant. So in that case, you have a very, very small error. Actually, in this particular case, this is a warranty road in Virginia where the accuracy was really high. I mean, even if you take a core with the variations in the thickness, you can get very easily 2 and 3% different in the thickness. So this one here tells you that it was very, very accurate when you were measuring it for a new pavements. So let me now move into a very interesting topic that we have been working on recently, which is the asphalt concrete density. As you all know, the asphalt concrete is composed of aggregate, air, and asphalt binder. And it's a very, very complex system. That's why I'm getting into the very small to the nano level to see the mastic itself and how the air voids. So it's very complicated kind of system. But density for us is very, very critical, because if you have a very low density, this means you have a lot of air void, and that will cause rutting. If you have a very, very high density, that might cause shoving for us. So either way, you cannot win. So we need to have a very good design specifically from the density point of view for our asphalt pavements. So it is most important parameters for quality control. So during the construction, the proper density is usually achieved by compaction, proper compaction, and trying to avoid above or under the exact compactions that we're looking for. So how do we measure density right now? Simply by taking cores, and these cores are kind of time-consuming, destructive, and so on. The nuclear density gauge, it has some errors and has been reported, and also it's a spot test. I don't know in Costa Rica how often you do that, but in the States usually depends on the state, between 500 feet, 1,000 feet. I don't know how often you do the nuclear gauge in measurements. Very often, yeah. So if you are doing it very often on the new design or new pavements, this means it's going to be time consuming. And of course, that's going to be maybe asking the compactor to do a little more after the material is a little cold. Then we have the non-nuclear density, which is the PQI. And this one here is also a spot test. And then we have the intelligent compactor. The intelligent compactor is very appropriate for granule materials, for soil, but for asphalt, it's a function of temperature. And as the asphalt is cooling, it's gaining strength, and it is depending on the strength or the modulus of the material. So it might not be the appropriate approach unless you have an excellent database for it. So let me go back to the asphalt concrete. In a simple way, gonna put it is, as I said before, electromagnetic waves has nothing to do with the strength or the modulus of the material, but it has to do with the volumetrics of the material. That will make it really easy for us to use it if we want to measure the density. So we look at the asphalt concrete and we try to measure the dielectric constant, and trying from that to measure what's the density of it. In order to do that, we need to look at each component, which means the specific gravity for each component, which is the air, the binder, and the aggregate. And also, we need to know what's the volume of the air, of the aggregate, and of the binder. Of course, we don't know what's the volume of the air because that's what we're looking for, right? Okay. So here the principle is very simple. Is the bulk dielectric constant of a mixture is a function of the dielectric constant and the volumetrics of the components. This is the equation. This is the last equation you're going to see. It's not that complicated, but I wanted just to mention that it's a function of few things. This is here the specific gravity, and this one here is the dielectric constant of asphalt. This is the dielectric constant of the binder. This is the maximum specific gravity of the material, and this is the dielectric constant of the stone, and this is the effective specific gravity of the stone. Of all this, the only thing that we really don't know, in my opinion here, is the dielectric constant of the stone. If we can get a good handle of this, then we'll be able to measure the dielectric constant and then the density on the go. So here's, in order to do that, we had a study where we put 6 lanes of pavements, and we put also copper plates for calibration, and they have different air voids. I'm just going to go a little quicker here to make sure that I'm on time. This is how the sections look like. And we collected GPR data. We obtained the dielectric constant of the asphalt, as I explained earlier. And from that, this is here the specific gravity of the asphalt. We know all this. This is the asphalt content. This is the specific gravity of the binder, which is 1.03. This is the specific gravity of the aggregate used. This is the maximum specific gravity, which we should know for any mix we place. And this is the dielectric constant for the binder, which is constant. And this is the only one that we don't know. And this is the one that we are measuring. So a simple way to do it, if I take a core, and I can back calculate the specific the dielectric constant of the stone, that will solve the problem. If I don't, then maybe if you are in an area here, let's say in San Jose, and we use a specific kind of aggregate, then I will know this dielectric constant of the aggregate, so I don't need to do that at all more than once. So from that, we can predict the GMB or the bulk specific gravity using the model. So this is here using the model. We collected data. You can see here the copper plates. We get a profile of the dielectric constant. We calculated the dielectric constant of the stone to be 6.1, and from that we came up now with the bulk specific gravity for the whole sections. So now I know the density for all my section. You can see here on this line, this is the calibrated value, and these are measured value, and they are all on the line. So that will tell you that this worked really well. The error we found is like 0.4%, 0.8%, 0.2%. It really worked very, very well. We took it to the field, and here showing you just 3 mixes: quartzite, 4.75 SMA, and sprinkle mix. Sprinkle mix, it's a limestone with a little coated quartzite on top for friction. As you can see here, the temperature has no effect whatsoever. We know that, but we want just to prove it to people who may question this. And this is as we compact, you can see that the amplitude here is increasing, which means the dielectric constant is increasing with each pass. So one of the advantages here is I can monitor the compaction, and I can tell the compactor, you know what, this is where you should stop. After 5 passes, you need to stop. So we took cores, we took nuclear, and just to share you with the results, this was accurate than nuclear in all these mixes. Somebody gonna ask the question. So I have 2 slides to answer that question. Say, during the compaction, we're using water. So what's gonna happen? This is the real problem, actually. So if you look during the compaction process, we always add water to cool the steel drum, right? And this water goes to the surface. If I have water, that's gonna affect my measurements. So this is the things that we're working on it right now. So we have testing where you have the asphalt concrete, and we sprayed some water on it, and we took the measurements as the water is drying. And this is, by the way, how we were doing some measurements in the field. This is a standby. This is kind of like measuring the density after each pass before you put it on a steel drum. And take measurements, lift it up, then put it back, and collect data. Okay? Now, if you look at the data here, you can see that there is a difference with and without moisture. The moisture is going to increase the amplitude that we have here. So this is going to be a problem for us. So I'm going to share with you where we are right now. This is a wet, so it's a higher amplitude. This is dry. This is the correct one, and this one is really a problem because of the moisture that we're using to cool the steel drum. What we found here is the antenna that you have here is most probably 1 or 2 gigahertz. When we say 1 or 2 gigahertz, it's not one single frequency. It's a band of frequency, but it's centered around that number. So in the case of 2 gigahertz, actually, this is the frequency, and it is centered around this number here. So we did look very carefully, and we found that this is here as the water is drying. This is here after 1 minute when it's wet, and this is when it's completely dry. So it's not affecting this frequency, but it's affecting that frequency. So that will make our job much easier. Let's go ahead and filter that data that it's very much affected by the moisture. And that's what we are doing right now. So if I go ahead and filter the data, the band between 0.2 and 0.8 gigahertz, I found that I have no effect on the moisture whatsoever. And that's the current research that we are doing in order to separate the moisture, because otherwise, I don't think that GPR can be used in real life. So this is one of the critical things that we were thinking about then. Actually, you can see here the surface reflection amplitude increased by 6.2% unless we took this out. So with that, let me summarize here what I just talked about this morning. I think that's my opinion that GPR is definitely a very, very effective technique. I think it should not be oversold in some of the applications because it is really doing a good job if we use it appropriately. It can provide quick and reliable information about the subsurface characteristics. And pavement layer thickness is not a big deal now to measure it. That's my opinion if we know what dielectric constant to use. The density prediction is a new area, and we need to be very careful of how to use it. I did try today to talk to you about the volumetric mixture theory as well as the impact of the moisture, because that's what's going to make it really effective in measuring the density. It can be used appropriately for the monitoring of the compaction in the field until the operator of the compactor went to stop. Effect of moisture, as I told you, this is ongoing things that we are working on, and I think we are really, I will call it myself that we really have kind of a little breakthrough in the signal analysis to isolate the moisture, because that was really a critical thing. So we're working on this right now as I speak. So with that, thank you so much for your attention, and I'll be more than happy to answer any questions.